Hello student, welcome back. We are going to start today's session. It is module 3, lecture 3. Satellite communication MECE106A. Shongita Roy, Assistant Professor, Electronics and Communication Engineering Department, Narula Institute of Technology. So today's content is satellite subsystems. It is power control, attitude control, tracking, antenna subsystems. Satellite subsystems. A communication satellite incorporates various subsystems whose functions in principle are distinct. It is customary to distinguish the communication payload or communication modules, antennas and repeater from the platform or service module that supports and powers the payload. The organization of a communication satellite platform is determined mainly by the following: the requirement of the communication payload, the nature and effects of the space environment, the performance of launchers, and the constraint which they impose. So this has the structure of satellite on board, antenna module, 3-stage repeater module, service module. Subsystems. The function of subsystems to provide and the most significant characteristics are indicated: minimum mass, minimum consumption, high reliability. So it is attitude control subsystem, propulsion, electric power supply, telemetry tracking already we have discussed in the earlier class, thermal control, structure already discussed. And these are the interfaces between different systems. The performance and specification of a particular subsystem depend on the presence of other subsystems, and this influences the interfaces between subsystems. Each interface is itself defined by numerous characteristics, of which the most typical are given in the figure above. Particular attention must be paid to the problems of electromagnetic compatibility and the nature. Numerous items of radio frequency equipment operating in different frequency bands at different power levels. So if these are the two subsystems, there are mechanical shocks are there like vibrations, thermal temperature, heat flux are there. So these are the different parameters that will affect when we are interfacing two different subsystems. Electrical, that is to voltage, current and power, magnetic fields and momentum, electromagnetic couplings and information rate and formats. They are the important parameters that governs the interfaces between two systems, means subsystems on board. Attitude control. Motion of the satellite can be resolved into motion of its center of mass in the Earth's center coordinate system and motion of the body of the satellite about its center of mass. The motion of the center of mass is characterized of the satellite orbit. Motion of the body of the satellite about its center of mass is determined by the evolution of the attitude. The attitude of the satellite is represented with respect to yaw, roll and pitch axis of a local coordinate system, and it will be shown subsequently. This coordinate system is centered on the center of mass of the satellite. The yaw axis points in the direction of the center of the Earth. The roll axis is the plane of the orbit and perpendicular to first and oriented in the direction of the velocity. So it is shown, if this is Earth, it is North Pole, it is South Pole, this is the axis and this is the equatorial line. So when the satellite is in the orbit, this is roll axis, this is pitch axis and this is the yaw axis. This is centered to Earth and this is in the orbit and this is in the pitch direction. Attitude control functions. The role of attitude control usually consists of mainly the mechanical axis in alignment with the local coordinate system to an accuracy defined by the amplitude of rotation about each of the axes. To be specific, typical ranges are 0.05 degree plus minus for a roll, and for pitch it is for pitch and plus minus 0.2 degree for yaw for geostationary satellite. In certain cases, a constant bias or a particular law of progression about one or more axes may be required in accordance with the requirement of the mission and the particular orbit concerned. Maintaining attitude requires two functions. The process generally involves measurement of the attitude of the satellite with respect to external references, determination of the attitude with respect to the local coordinate system, computation of the actuator commands, execution of the correlation by means of actuator mounted on the satellite, evaluation of the attitude in accordance with the satellite dynamics under the effect of actuating and disturbing torques. Attitude sensors. These sensors measure the orientation of the satellite axis with respect to external references such as the Earth, the Sun and other stars, or the progression of the orientation with time geometers. Their essential characteristics is accuracy. It depends not only on the procedure used but also on the alignment errors of the detector with respect to the body of the satellite. Sun sensors use photovoltaic elements which produce a current which illuminated by the sun. So it is the activity of sun sensors. They measure one or two angles between their mounting base and incident light. That is, to light means here sunlight. The accuracy obtained for measurement of the angle between the direction of the sun and an axis related to the satellite is of the order of 0.01. Earth sensor. The Earth surrounded by its atmosphere appears as a spherical black body at a temperature 255 Kelvin when its radiation is measured in the infrared absorption band of carbon dioxide 14 to 16 millimeter. As seen from space, the image of the Earth contrasts strongly with respect to the background plane, which has a temperature around 4 Kelvin. Measurement of infrared radiation, the emission of which is approximately uniform over the whole surface of the Earth by means of a thermosensitive element such as a bolometer, thermocoupler or thermopile, permits the contour of terrestrial globe to be detected. Star sensors. An image of a given portion of the sky provides a map of the stars whose relative position are detected and compared with the reference map. About 10 stars are tracked simultaneously. The measurement accuracy is high, that is to 10 to the power minus 3 degree of the order. This is a danger of saturation. Inertia units. Inertia units use accelerometers to detect translation motion of the satellite or gyrometers to measure the angular velocity about one axis. They are subject to drift and bias errors. Mechanical devices have a limit lifetime about 10,000 hours, which prohibits their continuous use for conventional mission of 10 years. Gyro lasers overcome these limitations. Now, radio frequency sensors. These sensors depend on measurement of the characteristics of radio wave transmitted to the satellite by ground radio beacons. They permit measurement of the angle between antenna axis on board the satellite and desired direction of the beacon. Radiation about the both sides, the yaw angle is difficult to evaluate. By measuring the rotation of a polarized wave from a single radiation beacon, a value of the yaw angle is obtained. Unfortunately, the orientation of the polarization is affected by Faraday radiation and the accuracy of the yaw angle is of the order of 0.5 degree. On other axes, the accuracy could be as small as 0.01 degree. Laser detectors. The use of a laser beam instead of a radio frequency beacon has been considered for determining the orientation of the satellite. The expected accuracy is 0.006 degree for roll angles and 0.6 degree for the yaw angle. One of the major problems lies in attenuation of the laser beam by clouds. Attitude determination. The purpose of attitude determination is to determine the orientation of the satellite in local coordinate system as defined in figure next in 11. For a rotational sensor, the line of sight of a particular object defines a cone which axis is the axis of rotation and whose vertex half angle is the angle between the direction of the object and the axis of rotation. Rotation of the sensor results either from rotation of the satellite on which the sensor is mounted or from scanning devices associated with the sensors. So this is shown earth contour detection. How the earth contour is detected. This is the satellite and this is the earth, and this is detecting the when it is revolving around the earth, it detects the contour of the earth. Determination of two possible sensor spins. So spin axis. So if this is a sun spacecraft and this is the angle with the sun, therefore the cone, the solid angle that is determined, and this is the center of the earth, the solid angle determined. So this is the possible spin direction depending on this sun cone and earth cone. Now the actuators. Modification of the attitude is generally obtained by generating a torque which, taking account of the dynamics of the particular satellite, causes an angular acceleration or velocity about an axis. The attitude control actuators therefore have the purpose of generating torques. Various types are available as follows. Angular momentum devices. Angular momentum devices include reaction wheels and gyroscopes which exploit the principle of conservation of angular momentum. With the reaction wheel, radiation rate d omega dt of the velocity of rotation of v of the wheel of the momentum of inertia I causes the angular momentum h is equal to I omega to be modified and the torque T aligned with the axis of the wheel is generated, and unit is Newton meter. So scanning sensor, this is the principle of the scanning sensor and how it is rotated, mirror rotating to subsatellite. This is the subsatellite point. So these are the diagram. Definition, measurement of parameters x, y. So this is the equation how the x deviation is evaluated, and this is the equation how the pitch or y deviation is calculated. Next, thrusters. Thrusters produce reaction forces on the satellite by expelling material or propellant through nozzles. The force obtained is a function of the quantity of material or mass ejected per unit time dm/dt and depends on the specific impulse ISP of the propellant used, and this is governing by this equation This is the force generated and unit is Newton. The torque obtained depends on the length L of the lever arm with respect to the center of the mass of the satellite. So torque generated is equal to force into distance Newton meter. The torque to be applied are of the order of 10 to the power minus 4 to 10 to the power minus 1 Newton meter. With the lever arm of 1 meter, the thrust are thus of the order of 10 to the power minus 4 to 10 to the power minus 1 Newton. In the interest of simplicity and reducing mass, these thrusters are generally part of the thruster assembly, which provides orbit control after installation in orbit. These thrusters often provide thrust greater than the values given above. Smaller thrust which can be varied are obtained by using thrusters in an on-off mode of the operation with a variable duty cycle. Magnetic coils. Magnetic coils with n turns of area S create a magnetic moment M is equal to NLS, ampere meter square, when fed with a current I. This magnetic moment can generate a torque of T with the terrestrial magnetic field B given by M into B, Newton meter. Solar cells. Solar radiation pressure applied to a surface of sufficient size is capable of generating non-negligible torque. In general, these are disturbing torque which are countered by designing the satellite so that the apparent surface in the direction of the sun is symmetrical with respect to the center of mass. The most significant surfaces are those of the solar generators. For instance, a satellite stabilized in 3 axes has 2 symmetrical panels which are aligned with the pitch axis. By modifying the apparent surface of the 2 panels of the solar generator, it is possible to generate torques about 2 axes. A torque about an axis in the direction of the sun is created by introducing a symmetrical bias between the normal to each panel and the direction of the sun. A further torque can be obtained about an axis perpendicular to the direction of the sun in the plane of the orbit by means of a bias of the one panel alone, asymmetry of the apparent surface. So this is given by this solar celling is given by this is windmill torque. This is no torque condition, this is unbalanced torque condition, and this is the sun detector. The principle of gyroscopic stabilization. Gyroscopic stabilization is obtained by creating an angular momentum on board of the satellite. By virtue of the principle of conservation of angular momentum, the orientation of the angular momentum tends to remain fixed in the initial space. By choosing an angular momentum aligned with the pitch axis benefits from gyroscopic stiffness, which preserve a fixed orientation in space in spite of momentum of the satellite in its orbit. Hence, movement about the roll and yaw axis are limited. So, this is the action of disturbing torque on a satellite. So, without angular momentum, and this is with angular momentum. So, satellite rotates at constant angular acceleration, while satellite rotates at constant angular velocity. So, here the acceleration is constant, here velocity is constant. So this is without onboard momentum and this is with onboard momentum. So obviously this is more stabilized condition. So the satellite with onboard angular momentum h about the axis y as consequence of the gyroscopic effect rotates about the x-axis at a constant angular velocity omega x given by this equation. The satellite without angular momentum starts to rotate about the z-axis with a constant angular acceleration d omega dt given by this. The satellite with onboard angular momentum h by y-axis as a consequence of the gyroscopic effect rotates about the angular velocity omega x given by this equation. Spin stabilization. Spin stabilization was used on early communication satellites such as numerous US national and export satellites, most based on Boeing 376 platform. The satellite is given a rotational movement speed of several tens of revolutions per minute, about one of the principle of axis of inertia. This is a simple process which benefits from the properties of gyroscopy but has the disadvantage of either leading to a rotating antenna with low gain antenna radiation pattern or necessitating contra-rotation of the antenna of the supporting platform. In the absence of disturbing torque, the angular momentum h remains a fixed direction with respect to an absolute reference frame. For a gyroscopic geostationary satellite, the axis of rotation is thus always parallel to the line of poles, that is to pitch axis. So the spin stabilization is showing over there. This is the antenna reflector, this is the antenna feeds, thermal radiator, control thruster, propellant tank, apogeekic motor, solar cell, battery pack, travel wave tube amplifier. So it is a microwave part. So discern repeater shelf, and this is the Boeing 376 configuration. Actuator implementation on a spinning satellite. So this is the spin speed control. Number 2 is this activation is attitude control about the roll and yaw axis. 3-axis stabilization. The term 3-axis stabilization denotes an attitude control system in which the body of the satellite maintains a fixed orientation with respect to the local coordinate system. It should be noted that spin stabilized satellites are also strictly described as stabilized in 3 axes since active control of the attitude about the 3 reference axes is provided. The nomenclature is thus a little restrictive. Satellite with onboard angular momentum or on wheel. The satellite contains a momentum wheel whose axis is aligned with the pitch axis in the nominal attitude configuration. The angular momentum generated about this axis provides gyroscopic rigidity, which tends to keep the mechanical axis of the satellite on which the wheel is mounted and the pitch axis coincident with the local coordinate system. Furthermore, by varying the velocity of the wheel slightly about its nominal value, correcting torque along the pitch axis are easily generated. Attitude control in normal mode is as follows. Pitch and roll angles are measured by one or more earth sensor operating in the infrared region. Gyroscopic stiffness conveyed by the momentum wheel enables movement about the roll and yaw angles to be limited. Pitch control is realized by enhancing angular momentum between the wheel and the body of the vehicle, that is by varying the magnetic coil or solar cells, which generates torque about this axis. The gyroscopic stiffness avoids measurement of the yaw angle. Indeed, in the course of the orbit, there is an interchange between the roll axis and the yaw axis every 6 hours, and this permits yaw control using the measurement of roll that was available 6 hours earlier. Therefore, it giving previous information also. So this is the attitude control of a body fixed satellite by a single momentum wheel. Spacecraft maneuver, thruster, wheel unloading 1 or 2, yaw control 3 or 4, roll control 5 or 6, north-south station keeping 5 plus 6, east-west station keeping 1 plus 2 or 3 plus 4. X bar indicates redundant thruster. This is the momentum wheel and this is the different directions are showing. This is the roll axis, yaw axis. With a single satellite with onboard angular momentum, several wheels. With a single inertia wheels, the axis of this wheel must be coincident with the pitch axis in the nominal attitude configuration in order to maintain a fixed orientation in space during rotation of the satellite in its orbit. Control with 0 degree of freedom, 0 to DOF, 0 degree of freedom. It is not therefore feasible to introduce a bias on one of the axes in order to change, for example, the direction of the antenna bore side, as this requires modifying the orientation of the angular momentum along the orbit, which translates into propellant consumption. Therefore, propellant consumption is very important because angular momentum uses huge amount of propellant. Control of the orientation of the spacecraft body is facilitated by using 2 or 3 wheels whose axes are inclined with respect to the pitch axis. The direction of the resulting angular momentum depend on the relative velocities of the rotation of the wheel and can thus be modified by adjusting their velocities. Depending on the number of wheels, 1 or 2 degree of freedom are introduced into the attitude control. An additional wheel for redundancy can be added. A configuration with 2 wheels in a V configuration about the satellite pitch axis in the pitch yaw plane and one orthogonal to the pitch axis for redundancy provides an additional degree of freedom. Indeed, the satellite could be rotated at virtually no cost about the roll axis by exchanging angular momentum between the 2 V-mounted wheels. This allows operation of the satellite into an inclined orbit while maintaining the appropriate pointing of the antennas by rotating the satellite to compensate the north-south displacement of the coverage. Now, satellite without onboard angular momentum. In spite of the constraint imposed by high dynamics of satellite attitude variation which require continuous control, it is feasible not to take advantage of the gyroscopic rigidity provided by installation of one or more inertia wheels on board the satellite. This permits considerable freedom in respect of the satellite attitude and allow the orientation to be continuously modified, for example, to shift the radio frequency coverage of the antenna or to compensate for the effect of the pointing displacement caused by a non-nominal orbit, that is to non-zero inclination. So we can conclude over there for today's class that this attitude and orbit control plays an important role how the satellite will be in the orbit. By controlling this, the satellite are stabilized in the orbit, or its momentum can be changed according to the requirement, and this is also associated with different other parameters like propellant, the interfaces, the magnetic field, all are interrelated, and the position of the earth and as well as the position of the sun, all are governed on the satellite to be on the particular orbit where it is. So this is an important parameter, or attitude control is an important factor for governing a satellite in the orbit. So today's class is up to this, and in the next class we will recapitulate this one and go to the beyond section. So we are concluding over there, and before that concluding, these are the reference for today's class. Mostly we follow the number 2. You can also follow other books. So, and I have already mentioned in the different slides the page numbers, so you can find from where we are studying. So we are concluding today's session. Thank you. We are ending the session.